Holding a grain of sand in your hand, can you see the universe hidden within it? It might sound crazy, but at the microscopic level, everything we know about reality changes. From the tiniest fundamental particles to the laws governing the vast cosmos, all are shaped by an incredibly strange world where matter simultaneously exists in multiple states, and the impossible is the norm. Today, we will dive deep into the universe in a grain to uncover reality's most astonishing mysteries. Welcome to SpaceTime's journey of cosmic discovery, where we explore the universe's deepest mysteries. In this video, we will delve into the topic, the universe in a grain, uncovering the laws at the microscopic level. Don't forget to subscribe to the channel so you don't miss out on other fascinating cosmic exploration videos. If you find this video interesting and helpful, please like and share to support us. When we look up at the star-studded night sky, or simply touch any object, we usually only perceive the world at the macroscopic level. This is the world of large, familiar objects that obey the classical physical laws of Newton and Einstein. However, behind the curtain of everyday reality is another universe, an incredibly tiny universe that holds the key to explaining everything. The universe at the microscopic level, where the strangest laws are the norm. This microscopic world is not just a miniature version of the world we live in. It is an entirely different space, where quantum physics reigns supreme and all conventional intuition is challenged. It is here that the most fundamental principles shape the structure and behavior of all matter, from the smallest atomic nuclei to the largest galaxies. All are shaped by these laws at the microscopic level. The journey to discover the universe in a grain began in the early 20th century, when scientists started to realize that classical physical laws could not explain the behavior of matter at atomic and subatomic scales. It was a crisis in physics, leading to the birth of quantum mechanics, an entirely new theoretical framework. Quantum mechanics opened a door to a completely different reality, full of surprises. Quantum mechanics is not just a theory, but also a philosophy of nature. It forces us to abandon familiar concepts of an objective world independent of the observer. Instead, it proposes a reality where probability and uncertainty are core elements. This is a profound shift in thinking, influencing all subsequent fields of science. One of the most astonishing and controversial concepts of quantum mechanics is the principle of superposition. According to this principle, a particle, like an electron, can exist simultaneously in multiple different states, for example, spinning clockwise and counterclockwise at the same time, until it is measured. Only when there is an interaction with the external world does the particle collapse into one of its possible states. Schrödinger's cat thought experiment is a classic way to illustrate the strangeness of this superposition principle.
In that experiment, a cat is placed in a sealed box with a quantum device capable of killing it. According to quantum logic, the cat would be both alive and dead until the box is opened and its state is observed. This shows the profound difference between the quantum world and the macroscopic world. Next is the phenomenon of quantum entanglement, also known as spooky action at a distance, as Albert Einstein once exclaimed. Two or more particles can become entangled, forming a single system, regardless of the physical distance between them. If we measure a property of one entangled particle, the other particle will instantaneously exhibit the corresponding property, as if information is transmitted immediately. This instantaneous correlation seems to violate Einstein's principle that no information can travel faster than the speed of light. However, experiments have repeatedly confirmed that quantum entanglement is real. Scientists have successfully created and maintained entangled states between particles hundreds, even thousands of kilometers apart, laying the foundation for technologies such as quantum computing and quantum communication. Heisenberg's uncertainty principle is another milestone, stating that we cannot simultaneously know both the precise position and momentum of a particle. The more accurately we try to determine an electron's position, the more information we lose about its momentum, and vice versa. This is not due to limitations of measurement devices, but is an intrinsic law of the very nature of reality at the quantum level. This principle has profound implications. It not only limits our ability to measure, but also suggests that reality itself, at its most fundamental level, is inherently indeterminate. Particles do not have fixed positions and momenta until we measure them. This is a major difference from classical physics, where everything is predetermined if we know enough initial information. Our universe is built from a small set of fundamental particles, the ultimate building blocks of matter as we know it so far. These particles are described in the Standard Model of particle physics. This model classifies particles into two main groups based on their roles: fermions, which are matter particles, and bosons, which are force-carrying particles, mediating fundamental interactions between fermions. Fermions include quarks and leptons. Quarks are fundamental particles that make up protons and neutrons, the components of atomic nuclei. There are 6 different types of quarks: up, down, charm, strange, top, and bottom. These quarks have fractional electric charges and only exist inside larger particles due to the strong nuclear force confining them. We can never observe a single quark in nature. Instead, we see them combine into composite particles called hadrons. A proton, for example, is made up of 2 up quarks and 1 down quark. A neutron is made up of 1 up quark and 2 down quarks. The stability of matter depends on this strong binding. Leptons include electrons, muons, taus, and 3 corresponding types of neutrinos. Electrons are the most famous particles. They orbit atomic nuclei and are responsible for chemical reactions, generating light and electric current in our electronic devices.
The movement of electrons through a conductor is the electricity we use every day. Neutrinos are extremely light particles, almost massless, and interact very weakly with other matter. Billions upon billions of neutrinos from the Sun continuously pass through our bodies every second without causing any significant interaction. Studying neutrinos helps us better understand the processes inside the Sun and other cosmic phenomena. Bosons are particles that mediate fundamental interactions between fermions. For example, the photon is the carrier of the electromagnetic force responsible for light, radio waves, X-rays, and all other electromagnetic phenomena we observe. Everything from seeing colors to using mobile phones relies on photons. Gluons are the force carriers of the strong nuclear force, holding quarks together inside protons and neutrons and keeping atomic nuclei stable. The strong force is the strongest force in nature, but has an extremely short range. Without gluons, atomic nuclei would immediately disintegrate and matter could not exist. The W and Z bosons carry the weak nuclear force, responsible for radioactive decay, a crucial process in the operation of the Sun and stars. Beta decay, a type of radioactive decay, transforms neutrons into protons, or vice versa, by emitting W and Z bosons, thereby producing neutrinos and electrons. The Higgs boson, discovered in 2012 at CERN, is a special boson. It does not carry a force, but creates an invisible energy field that permeates the universe, called the Higgs field. Particles interacting with the Higgs field acquire mass, explaining why some particles have mass while others, like photons, do not. The existence of the Higgs field and the Higgs boson was a significant milestone in completing the standard model of particle physics. It provided an explanation for the origin of mass of fundamental particles, one of the biggest questions in particle physics for decades. This discovery confirmed almost the entire standard model. The standard model of particle physics is the most successful theory of modern physics, describing all known fundamental particles and 3 of the 4 fundamental forces of the universe: the electromagnetic force, the strong nuclear force, and the weak nuclear force. This model has been confirmed by countless experiments at particle accelerators like the Large Hadron Collider, LHC, with incredible precision. It allows us to predict experimental results with high reliability, from predicting the existence of new particles before they were discovered to accurately calculating particle interactions. The standard model is the pinnacle of understanding matter and forces at the most fundamental level, a grand achievement of science. However, the standard model is not perfect. It does not include gravity, the force we feel most clearly in daily life, and the force that dominates the universe on large scales. Integrating gravity into a quantum framework remains one of the biggest challenges in theoretical physics, known as the problem of quantum gravity. Physicists are actively seeking a unified theory, a theory of everything, that can describe all 4 fundamental forces and all particles within a single framework. Prominent candidates include string theory, M theory, and loop quantum gravity, each offering bold and profound ideas. Quantum field theory is the theoretical framework upon which the standard model is built. In QFT, particles are not distinct entities, but rather excitations of fundamental quantum fields that permeate spacetime. Each type of particle has its own field. For example, the electron field creates electrons, and the photon field creates photons. These quantum fields are never static, even in an absolute vacuum. They are always continuously fluctuating, creating and annihilating pairs of virtual particles and antiparticles in an extremely short time. These virtual particles constantly appear and disappear, playing a crucial role in mediating forces and even preventing a vacuum from ever being truly empty. The Dirac-Sea phenomenon in QFT describes that the vacuum is not empty, but filled with negative energy electrons. When a positive energy electron is created, it leaves a hole in this sea which we observe as an anti-electron, positron. This provides an explanation for the existence of antimatter. Understanding the laws at the microscopic level is extremely important for exploring the origin and evolution of the universe. Immediately after the Big Bang, the universe was extremely hot and dense, containing only fundamental particles and quantum fields. It was these quantum interactions that shaped the structure of the early universe, thereby creating the first elements like hydrogen and helium. The strong and weak forces, along with the electromagnetic force, determined how the primordial particles combined to form protons and neutrons, and then the first atomic nuclei. Everything we see today, from brilliant stars to rocky planets, originated from the quantum processes that occurred in the first few minutes after the Big Bang. The cosmic inflation phase, a hypothesis suggesting that the universe expanded extremely rapidly in a very short moment, about 10 to the minus 32 seconds after the Big Bang, is also explained by particle physics. During this phase, a quantum field called the inflaton field drove the expansion, making the universe homogeneous and flat. Tiny quantum fluctuations in the inflaton field during the inflatory period were amplified to macroscopic scales, creating the seeds for the formation of galaxies and the larger structures of the universe we observe today. Without inflation, our universe would be very different. Perhaps there would be no life. Even black holes, which Stephen Hawking deeply studied, have important quantum aspects. Hawking radiation, a theoretical phenomenon where black holes are thought to emit particles due to quantum effects near the event horizon, shows a deep connection between quantum physics and general relativity. Hawking radiation suggests that black holes are not truly black, but can gradually evaporate over time, an extremely slow process, but with profound implications for the ultimate fate of black holes. This phenomenon is one of the strongest indications of the need for a unified theory of quantum gravity. Thanks to quantum physics, we have invented many groundbreaking technologies, from lasers, transistors, microchips, to smartphones and modern computers. Every time you use an electronic device, you are interacting with a product of quantum mechanics. These technologies have completely transformed our daily lives. Nuclear magnetic resonance, MRI, and other medical diagnostic tools are also based on quantum principles of atomic nuclear spin. By manipulating and measuring these spins, doctors can create detailed images inside the human body without surgery. This is an extremely valuable medical application of quantum physics. Quantum computing, a promising field of research, uses the principles of superposition and quantum entanglement to process information in an entirely new way. Instead of binary bits, 0 or 1, like classical computers, quantum qubits can be 0, 1, or both simultaneously, allowing for parallel processing and exponentially increasing computational power. The potential of quantum computers is immense, from breaking current encryption algorithms to simulating complex molecules for drug research and new materials. Although still in its early stages, quantum computing promises to revolutionize many industries in the near future. Quantum materials, another burgeoning field, explores materials with special properties due to quantum effects at the atomic and molecular level. Superconductors, superfluids, and topological insulators are typical examples. These materials could have groundbreaking applications in lossless power transmission and next-generation electronic devices. The laws of the universe at the microscopic level often go against our common intuition, but they are the most fundamental laws. They remind us that reality is far more complex and wondrous than what the naked eye can see.
The scientific philosophy from Carl Sagan always encourages us to embrace wonder and curiosity about the unknown, always questioning everything. Carl Sagan once wrote in Cosmos that we are a way for the cosmos to know itself. And it is through understanding the laws at the microscopic level that we are gradually deciphering ourselves, our origins, and our place in a vast, mysterious, and awe-inspiring universe. Sometimes, to understand the greatest, we must start with the smallest. A particle, no matter how tiny, contains an entire universe of rules and interactions, shaping the nature of space, time, matter, and energy. It is vivid proof of the unity and beauty of natural laws, a complete picture that we are gradually painting. Microscopic physics is not just about finding the smallest particles or the fundamental forces. It is also about discovering a new way of understanding existence. It raises profound questions about the nature of reality, whether it is objective or dependent on our observation, and about the role of consciousness in the universe. From the Standard Model to quantum field theory, every step forward in exploring the microscopic world opens new horizons of knowledge. These discoveries not only enrich scientific understanding, but also challenge the limits of human imagination, expanding our vision of what is possible. We have learned that the universe is not a rigid, predictable collection of objects like a mechanical clock. Instead, it is a complex network of fields and energy, where everything is deeply connected and constantly interacting. Even the smallest particle carries the imprint of the entire universe. Looking at a grain of sand, we don't just see silicon dioxide. We see billions upon billions of atoms, each a miniature universe, with electrons moving in probabilistic orbits. Inside the nucleus, quarks dance, confined by gluons, all obeying strange and inseparable quantum laws. Every interaction, every event at the microscopic level is part of the grand cosmic symphony. From nuclear fusion reactions in the sun's core providing energy for life on Earth, to the radioactive decay of heavy elements generating heat in Earth's interior. All are manifestations of quantum forces.
Scientists continue to search for new particles and unknown interactions to complete the picture of the microscopic universe. The search for dark matter and dark energy, the mysterious components that make up about 95% of the universe, will also lead us deeper into the quantum world and theories beyond the standard model. Dark matter, although it does not interact with light, its gravitational influence is very clear in galaxies. Modern theories suggest that dark matter may be composed of new, undiscovered quantum particles. Deciphering this mystery is one of the top goals of particle physics. Dark energy, a mysterious force pushing the universe to expand ever faster, is also a quantum concept. Scientists speculate that it may be related to the vacuum energy of quantum fields, a challenging idea, but one with the potential to explain the accelerated expansion of the universe. We can say that our universe is a gigantic quantum universe, where the most wondrous laws are also the most fundamental. Although we cannot see them directly, we still feel their widespread presence and influence in every aspect of life in the entire structure of the cosmos. Human curiosity is the main driving force behind these discoveries. Stephen Hawking, with his research on black holes and the origin of the universe, pushed us to think about the limits of understanding. He sought to combine quantum mechanics with general relativity, though not entirely successfully, but opened many new avenues of research. Every new discovery about fundamental particles or interactions is an important piece of the puzzle, bringing us closer to a unified theory of all forces. That is the great dream of physicists, a theory of everything that can describe everything in the universe from the smallest particle to the largest structure. Imagine one day we could describe the entire universe, from the Big Bang to the formation of galaxies and the evolution of life, with just a few fundamental equations at the particle level. That would be the pinnacle of scientific understanding, an achievement that could completely change how we perceive everything.
Concepts like space and time might also not be continuous at the Planck scale, the smallest meaningful limit in physics. There, space and time could be quantized, becoming discrete particles or quanta, a revolutionary idea about the nature of space-time itself. This means that even the very fabric of space-time, which we consider a solid and continuous foundation, could be a product of quantum interactions. The universe is truly a dynamic structure, woven from invisible threads of quantum energy and information, creating a complex tapestry of reality. The quantum world offers continuous surprises, challenging our deepest preconceptions about a stable and easily understandable world. It teaches us humility before the infinite complexity of nature and expands our vision of what humanity can discover and comprehend. Exploring the universe in a grain has shown us how microscopic laws shape reality. But there's another force, an invisible glue that has been and continues to connect all matter, from distant planets to ourselves to the Earth. In our next video, we will unveil the mystery of gravity, the glue that binds us to Earth. Don't miss it.